Hello and welcome. This video is designed to unveil some of the more in-depth information on the electro-mechanical design of power meters and why you might think they are expensive compared to the rest of your bicycle, which let's face it, it's a pretty bit of basic engineering. It's going to be pretty heavy on information, so if you don't want to sit through it, please leave. I don't want to waste your life. So quickly look at the principle of power. Power is measured in watts or joules per second, and it is the rate of energy expenditure or energy divided by time. Also be expressed in calories per second or joules per second. Electrically it can be expressed as voltage times current, but in the mechanical sense, which we're dealing with here, like anything that's rotating, we calculate power by multiplying the torque by the rotational speed, so Newton meters times radians per second. Now a radian is just a measure of, it's a unit of angular measure, so 1 radian equals roughly 57 degrees, so radians per second is 57 degrees per second. It's just a unit of rotational speed we use to work out power, and that's the unit is watts or joules per second. If you have RPM, you can convert RPM into radians per second by timesing it by 2 pi over 60. So power, why do we care about it in cycling? Power's probably the most reliable human performance metric there is in cycling. Heart rate, average speed, etc. can change with too many variables: wind speed, gradient, caffeine intake, fatigue, and even adrenaline. You know, like if you're going around a corner, going up a climb, and you see someone ahead of you, I know my own heart rate might jump 5 or 10 beats per minute with some endorphin release or adrenaline release. I don't quite know with chemical what it is, but the power won't necessarily change. But I can see my heart rate go up. But power can be used to consistently quantify training productiveness and track improvements or weaknesses. And I think that's a nice little summary how you would sum it up, really. Another really important metric is power endurance, which is power over what time period, which is essentially energy. This is a good metric for biomechanical analysis, like bike fitting. Power could be measured in, or power endurance could be measured in watt hours, just basically like a battery. And if you do this for an hour, this is essentially your functional threshold power. So let's say your functional threshold power is 300 watts for an hour. That's less than a basic e-bike battery. Or you'll be able to go on a little bit longer after that hour's up. You'll be able to go on a small power output where a battery won't, but it's essentially the same. It's basically your capacity. It's the same sort of metric. So on this page, I've got a little matrix of all the power meter types I'm going to discuss in this video. I've chosen to stick to crank or sort of chain set power meters, and some of those that I think you should be considering are in this table. Note I've left out pedal-based power meters. I consider pedals as a semi-consumable product. They wear out too quickly, too many moving parts to be used as a sensitive transducer in my eyes. So just quickly looking at this table, I've got all the different types of power meter down the left column, and I've got the type, whether they're spider, axle or crank. I've got if they're left and right leg, and also if they're left and right leg on common transducer, common circuit or different circuits, which I'll explain more later. I've got the strain gauge layout, signal to noise ratio, and the resolution and sensitivity of the sensors, and how they differ. I'll explain that later. Sort of perceived reliability, this is a bit of a guess because I haven't owned all of these power meters. I don't know for myself, but just from sort of reading and market reaction sort of thing, and a price rating as well. So we can come back to this table perhaps later. So then the third main heading, if you like, of this is you have to understand the load cases of what a chain set or a power meter needs to measure. And in all systems pretty much strain gauges are used, whether they're strained longitudinally or in shear, we'll come to later. All use variations of a Wheatstone bridge circuit, whether it be quarter, half or full. I'll explain that as well, what that does and how that is really beneficial for this type of sensor. Different Wheatstone bridge circuit types can offer high resolution or signal to noise ratio, the opportunity for temperature effect compensation, and bending and twisting strain compensation as well, and how they manage parasitics. Again, I'll explain all of that. Now, essentially the chain set sees many different loading scenarios, and we are only interested in measuring the pure torque that gets transferred to the chain and propelling us forward. There are many other types of loading which we call parasitics, which we want to avoid sensing. Largely these can be avoided by gauge selection and the Wheatstone bridge selection, and modifying the geometry of the chain set or the crank, i.e. placing gauges away from areas of high parasitic strain. Again, I'll go into more depth about that. So let's quickly look at what strain gauge is first of all. So a normal sort of longitudinal strain gauge is a strain gauge is essentially a small metal foil contained in a very thin polymer or plastic substrate. They're inherently flexible and can easily be bonded to metallic surfaces to pick up surface strain. Now, surface strain in the material causes a change in length in the metal foil. This gives rise to a change in electrical resistance of the component, which can be measured as a voltage change when put in a Wheatstone bridge circuit and converted to mechanical strain using the gauge factor of the strain gauge. Normally the strain gauges are aligned parallel with principal loading. So let's have a quick look at a different type of gauge. This is a shear gauge. Now, a shear gauge is used to measure strain due to torsion or shear strain. The gauges are aligned normally at 45 degrees to the principal loading, e.g. on the axle of a crank. They'd be aligned sort of 45 degrees to the axis of the crank, if you like, like the rotor in power. One grid of the sort of dual grid gauge goes into tension, which is positive strain, if you like, and the other one would go into compression, which is negative strain. So for this type of gauge, you've got essentially a double resolution, because you've got the two signals going opposite way. So your magnitude of your signal goes up by 2. So down the bottom there you can see a diagram of a Wheatstone bridge type circuit. And what is this Wheatstone bridge thing that people talk about when they're instrumenting with strain gauges, and why is it good? Well, a Wheatstone bridge circuit is a divided bridge circuit used for the measurement of static or dynamic electrical resistance. The output voltage of a Wheatstone bridge is expressed normally in millivolts per volt input, which can be, in this case, in a cycle power meter given by a battery with a voltage regulator, like a watch cell battery. That is your voltage input. The Wheatstone circuit is well suited also for temperature compensation. So you want your power meter to be reading the correct wattage amount or torque amount for any different sort of ambient temperature you're using it in. Now, the number of active strain gauges that should be connected to the bridge depends on the application. For example, it may be useful to connect gauges that are on opposite sides of a beam, one in compression and the other in tension. This is the case with the shear gauge I just explained. In this arrangement, one could effectively double the bridge output for the same strain. So you're essentially doubling the resolution there. In installations where all of the arms of the bridge are connected, temperature compensation is automatic, as resistance change due to temperature variations will be the same for all of the gauges in the bridge. And you'll see that most of the power meters I'll discuss have this feature. So it doesn't matter if the temperature changes, because all of the resistors in the circuit will change by the same amount. That's the goal anyway. Now, this is where it gets complicated. So let's discuss the load cases on a crank, and the desired loads that you want to measure and the parasitic loads we don't want to measure. So, as I've already mentioned, we are only interested in measuring the pure torque that gets transferred into chain tension that will propel us forward. There are many other types of loading on the chain set that we want to avoid sensing, which do not contribute to our forward motion. These can be called parasitics. You may think it's easy to sense this pure torque on the cranks, but if we look a little closer, one can realise it becomes a very messy picture, comprising of lots of other forces and moments. If we do not attempt to filter these parasitic forces out, they will contribute to our strain signal and muddy our vision of what we actually want to measure. So, If we look at the picture, I have added some arrows to represent some of the forces that will give rise to strain on the crank. Essentially, we only want to measure the strain due to the loading represented by the red arrow. This is the applied force that gives rise to torque on the chain set and thus tension in the chain, which propels us forward. However, we can see some other parasitics present. We have axial twisting of the crank due to the lever arm of the pedal axle. At 3 o'clock, this will try and sort of wring the crank like a wet towel. And at 6 o'clock, the same force is trying to swing the crank inboard under the bottom bracket towards the centre plane of the bike. Also at 6 o'clock, we have an axial component due to your weight pulling the crank directly down, which contributes to no power at all. So how do we avoid all of these bad forces and the strains that come from them? Largely by two methods, as I already said. One, gauge circuit in selection and placement. And two, we have the option to modify the geometry of the crank and place the gauges where these parasitic strains are low or can be cancelled out. So let's look at some of the examples of how the brands do this. So, sensor application of each brand. Firstly, let's look at the golden standard SRM. People often disregard due to high price, and like high-end AV, equipment, it's certainly a case of diminishing returns. But in this case, you are buying the most accurate. It's probably got the highest signal-to-noise ratio by some margin, with 16 active gauges on a 4-arm spider. The electronics are highly optimised to provide good battery life with what would normally be quite a high-power circuit. Earlier types, as seen on the left picture, feature a full bending bridge on each arm. Now we have a full shear bridge on each arm. This offers unrivaled resolution, temperature and bending compensation. All units have a dynamic calibration at different temperatures, and a dynamic calibration rig is assembled with a full chain and group set, and calibrated mechanical or hydraulic brake is used to provide the torque. Obviously the brake load has to be the brake load cell has to be of high accuracy to provide reliable and a stable reference torque and thus power figure. This is not such an issue with static calibration using weights, although static calibration is not normally as accurate in this application. So, little diagrams at the bottom there. You've got the bending bridge setup of the gauges on the older type SRM, and on the newer type SRM you have a full bridge, Wheatstone bridge set up on each arm of the spider with 4 active grids, if you like, on each arm, 2 on the top surface and 2 underneath. Next sensor application, Quarq. So I'm going to discuss the new Quarq D0 and D4s. Just a quick summary. On this one, it's very similar to the SRM. You've got 5 gauge pairs on a 5-arm spider. So instead of a 4-arm spider, you've got a 5-arm spider. So there's 10 active grids in total, but only applied on one side of the spider. I asked the SRM engineers, the Quarq engineers, does the D0 and the D4 have the same, essentially the amount of strain for any given torque, which would affect the strain resolution of the different power meters? And they said yes, the strain resolution on all types is the same. Now the difference with this is that the gauges are sort of pre-populated on the printed circuit board, making the application of the individual gauges much quicker and easier. It also provides a cost saving, because you don't have to spend all the time aligning by eye and aligning by hand each individual gauge. And they're claiming it's accurate to 1.5%. Probably got the easiest battery install out of all of the power meters. It's Bluetooth and ANT+ enabled and comes with an app. One other thing I'll just quickly mention is that the electronics in this are not potted, so they're not engulfed in an insulating polymer, but I'll discuss that in a minute. The new Quarq is proving to be really popular in many markets, as it's probably the cheapest spider-based power meter apart from the NG Eco. I spoke to some SRAM people at Eurobike and they said they couldn't make them fast enough, basically. Power2Max also said this about their NG Eco, so it's really good. There's some real competition at this price level. It's also one of the lightest available, with essentially the SRAM red hexagon carbon crank attached to every spider. Now, one thing that does concern me is this large air cavity sealed inside the unit, as it's not potted. the black circular cover that waterproofs the unit from the outside is sealed at the edge with a sort of a thermal releasing glue for ease of factory service, the similar type of glue that you get around your iPhone screen, I think, that goes soft when you heat it up. This, however, means that the electronics are not potted and leaves the potential for kind of cyclic condensation and evaporation on the PCB components when transferring the device from varying temperature environments quickly. The other downside for me is that there's no Shimano 24mm steel axle type available. You either have a 30mm axle or a GXP axle. If you have a 86mm BB type, like a standard Shimano bottom bracket width, you can't really run the 30mm axle reliably, and the GXP method of constraining the non-drive side bearing has never really, to me, been a good solution. You can buy a dual row bearing from Rotor or Enduro to fit a 30mm axle in a 46mm shell, but when you do the calculation, the actual ball bearings end up being about 1.6mm in diameter, and that's just too small. They won't last. So, and the fact that the proper bearing suppliers like SKF, NTN do not make a bearing like this just goes to show it's not going to last. So with this one, you are really limited to BB30, or if you really like it, GXP. And if all of your bikes are the BB30 standard, then the BB386 Evo option is the one to go for, because that's going to fit every 30mm standard. But yeah, I really like the Quarq, and it's doing good to drive down the price of the Spiders, and it does share a lot of the technology with the SRM. It doesn't have probably the signal to noise ratio of the SRM. It doesn't have as many strain gauges as the SRM. But yeah, it's quite a neat unit. It's just a shame they don't do it in 24mm. Now, next unit, Power2Max, everyone's favourite, sometimes. Now, they've got 3 current models, the NG, NG Eco and Type S, which is actually ending production around about now. They've all got 2-arm spiders instead of a 4 in the SRM or a 5 in the Quarq. That doesn't really matter, because they'll all work with the same amount of strain depending on sort of width or the geometry of the arm of the spider. The NG and NG Eco have got full bridge, so you've got automatic bending and temperature compensation in those. The NG, the top end NG one, is calibrated dynamically on a dynamic rig, and that helps it get to a plus or minus 1% accuracy. The difference between that and the Eco is that the Eco only undergoes a static cal only with dead weights, and that's, they state that as a plus or minus 2% accuracy, so you are paying for the extra accuracy with the NG. You also get a built-in battery which is rechargeable, but for me I actually like the removable one of the NG Eco, because with the built-in battery, that life is going to degrade over time with the number of cycles, and then what do you do with it when it's degraded? But at least with the watch type battery and the NG Eco, you pull that out, shove a new one in whenever, and it's quite easy to diagnose faults with it. If you suspect the battery in the NG is bad, you can't service it yourself. If you suspect the battery in the Eco is bad, just put a new one in and try it. They both support left and right sort of readouts, although it's the left and right thing is kind of done with a prediction algorithm, because and it's the same with SRM and Quarq. If you take one leg off the pedal, let's say you unclipped your left leg and you just pedalled with your right leg, now you know that 100% of your power is going through your right leg, but the head unit will never say that, because it has to fill in some data, because it doesn't always know at what rotational angle the leg is putting in the power, if you see what I mean. So it's kind of, they have to use a bit of software to fudge the figures. So it's not true left. None of the Spider Betty's power meters are true left and right, because it can't for sure tell what leg is putting the power in, because the left and right leg are sensed off the same transducer. But I'll explain more about that later. So yeah. And actually my favourite one is the Type S. Unfortunately it's ending production soon. The difference with this is it's actually a half bridge circuit, and so it doesn't have automatic temperature compensation from the Wheatstone bridge. They use a very expensive thermal compensation resistor in addition to the strain gauges. Now, when I asked one of the directors of Power2Max, they said that this resistor was about €6 a piece. And if you imagine, actually, in terms of the other components on the PCB, that's quite expensive. And if you go through a batch of 20 and you mess 5 up by fucking up the soldering, it's quite an expensive piece. So that they were trying to get away from that. Also on the Type S, it was only a static calibration only. Still 2% accurate. ANT plus only, no Bluetooth and no app. So difficult to do firmware, although you never really needed to do firmware with the Type S. So this whole firmware app thing is just a bit of value added shite that you don't really need. That's why I like the Type S, it was pretty simple. One other thing to say, yeah, but unfortunately the Type S has been phased out. And the new NG and NG Eco have gyros to do cadence, not accelerometer as in the Type S. So I've put that in there, I think. Yeah. So the gyro can provide better instantaneous angular velocity sampling, and is also more accurate with QU rings, I'm told by one of the directors from Power2Max. Now the thing is, with the Power2Max, they are slightly heavier than the other spiders, but not by much, maybe like 40 to 50 grams, because all the electronics are fully potted with polyurethane, which is really good for insulation and sort of weatherproofing. And there's also not much machining of the sort of superficial bits of the spider to save weight. This possibly could be to do with keeping the rest of the spider stiffer, to stiffen up the chain rings, so there's not so much parasitic bending when the chain is pulling the chain rings at different angles. Also, there's a huge range of cranks supported. Unfortunately, most of them are 30mm spindles. Only one supports the 24mm Shimano crank bottom bracket type, which is the Rotor 3D24. But I've been told by Rotor they're phasing this crank out too in the coming months. And unfortunately, the weight of this combination is more than a 5236 Ultegra chain set, which comes about 750 grams, and the weight of that combination that I just explained was about 790 grams. And when you're spending like €700, €800, it seems a shame to be adding, I know you're adding the functionality of power, but it seems a shame to be adding weight as well. And when I did meet one of the directors of Power2Max, he was a very technical guy, and he was so enthusiastic about the electronics. It was like really refreshing to see, when most people you meet who are the sort of the faces of these brands are sort of very marketing based people. It was really good to meet a really technical owner. Yeah, so I think I've got a little video of the NG Eco with the 3D24 crank and the old Ultegra chain rings, which they're still supporting, but there'll be a new NG Eco for the new Ultegra because the bolt pattern is slightly different. And I like this crankset because it's got the same preload system as a Shimano bottom bracket. You preload it from the non-drive side cap that threads into the end of the crank. Really simple, really easy to remove swap between bikes. So, next brand, Rotor, in particular the Rotor 2-in Power, which is their flagship power meter. So this is different because it does do left and right, but it does it on two different transducers. So along with the dual-sided new power meter from Stages and 4i, etc., this is a true left and right solution, as you're sensing each leg on a different circuit. So in the axle you have a shear gauge arrangement to sense your left leg, and in the drive side crank you've got a full bending beam layout. So you've got longitudinal gauges, 2 tension gauges on the top, 2 compressional gauges in the bottom, and I've drawn some little lines, those orange lines, if I get the mouse, there, I reckon that's where the gauges are. And you've got your shear gauges. Actually they're not inside the tube, they're under this sticker. I found that out from Rotor. I always thought they'd be protected inside the axle, they're not. There's a slight machining in this axle, so it's very slightly under 30mm there. They put the gauges on, they drill a hole, the wires. The wires go inside the axle, and then they put the sticker over the top. So that does left and right on different circuits. Now that's great because it gives you a true left and right balance. The only thing is, because you're sensing on two different basically strain gauge circuits, is that you hope that they've calibrated them so that the sensitivity or the gain of those two sensors is exactly the same. Otherwise one leg would overread the other leg, but you know, that's just a risk you take by using two different circuits. Yeah, I like Rotor, but I struggle to see how they survive as a company. I bet they're hemorrhaging cash. They have really nice products, all quite high end, but they must have huge production costs. All the CNC is done in Spain. Must have high R&D costs. They're pretty low volumes, and they must have a lot of very loyal investors, let's say like that. And I think this circuit is quite high power consumption, because you use a AA battery for this circuit, and that's quite hefty compared to the little watch shells like they used in the other power meters. The axle is 30mm. It's sort of the universal 30mm, so it's long enough to fit any shell, whether it's BB Right, BB30, BB30A, anything. Can't really use it in an 86 by 46 Shimano shell, because as I mentioned, with the Quarq, the bearings are going to be too small, and there's no 24mm rotor power meter available, because I think the strain on the steel axle is too low for them to get a good signal. But yeah, they don't make that, only a 30mm. I'm not sure if this is a static or dynamic calibration. Didn't manage to find out. Okay, so next, probably the most popular, because of the price point, Stages, and also is very similar application of 4i. So on the let's look at, let's say, a 105 Dura Ace Ultegra aluminium crank. You've got a full bridge, which is 4 strain gauges, all linked to the same Wheatstone bridge, all going into shear. You've got 4 little gauges in a rosette pattern on each crank, with 2 of the grids placed either side of the centre line. So if you look down the length of the crank and you drew a centre line, you've got 2 grids above it, 2 below. So essentially now you've got what's called a shear beam load cell. The stages are mostly done on alu cranks, although some carbon cranks are now available. The strain resolution on stiffer carbon cranks is lower, because for the stiffer material you've just got less strain for the same torque, which in my opinion is not ideal, because your signal is not going to be as good if you've got less strain. Signal to noise ratio goes down. So for good sensor resolution, you essentially want as much strain as possible. So if you've got a stiffer crank, you're going to get less strain. It's more difficult to obtain a repeatable and reliable transducer from a carbon crank, also because of hysteresis in the epoxy on the surface and also within the laminate. Now, I found out from Stages that they buy the carbon cranks from Campagnolo, direct from Campagnolo, without the clear coat, without the top layer of epoxy, to get around this issue. So they bond the gauges down and then they clear coat the unit. Now, what I've always worried about with Stages application is the bending compensation. So how, impervious is it to parasitic strains from all sorts of different bending, which we've highlighted earlier. And surprisingly, there appears to be really good bending compensation from this gauge layout, as can be seen in one of the videos in a minute, where I try to bend the crank and analyse the output by looking at the torque just on their little app. The bending compensation seems to work quite well. It's a little bit noisy, but you're going to get that with anything. Now, to provide the good bending compensation, that's why they've used the 4 shear grids in the layout that I described. And the gauge position here is critical for the gauges on opposite sides of the bridge to have equal cancellation. So they have to align those gauges about the centre line of the crank very carefully, otherwise the gauges won't cancel out equally. You'll also notice on the Campy carbon crank, which I'll show in a minute, that there's an extra part to the plastic cover wrapping around the top and bottom side of the crank. So I asked Stages, what's this? And they said they actually have to have an extra 2 strain gauges, or an extra 2 grids. So you now got 6 in total on the carbon crank. They have the normal shear rosette on the side of the crank, like all the others, but they also have a half bending bridge arrangement on top and bottom with the 2 extra strain gauges. So why do they do this? Well, they said that the carbon cranks from Campagnolo are joined in production somewhere down the centre line of the crank, on the inside face, and that this join was not always uniform or in the same place, and a 4 shear gauge rosette was not accurate or repeatable enough. So this is why they had to compensate with an extra 2 gauges that would just measure bending alone. With a more uniform material like aluminium, it's much easier to predict the neutral axis of bending and accurately align the gauges about this centre line. So in my opinion, don't buy carbon Stages. The strain resolution is too low, and there may be long-term issues with hysteresis or viscoelastic creep of the sensor due to changes in the epoxy. Finally, the Stages and 4i and Pioneer power meters are all kind of piggyback solutions. You know, cranks were designed to be cranks, not transducers. The cranks are not modified or optimized to be proper torque transducers, so the strain signal will never be as good. Strain gauges are a couple of quid, accelerometers, pence, PCB, you know, a couple of quid, so you're paying for the labour, which has to be skilled. And this is the carbon Cambi crank that I was talking about. Now up here you can see the extra part of the cover, which covers the extra bit of the strain gauge. Because the strain resolution on this was too low, we had to put some more on it.
The carbon? Oh, okay, for sure. There's a carbon crank stiffer than the other. So when you are doing or instrumenting other carbon cranks, the strain is lower than the aluminium cranks, so it's different. So the signal is also good.
You mean the signal from power meter to the head unit?
No, I mean when I say signal, I mean the strain resolution
From the strain gauges?
Yeah. It's lower.
He used the different strain gauges.
Oh, okay. Thanks very much.
So you can reluctantly hear at the end of that video the Stages engineer confirming that the strain resolution from carbon cranks is lower. And in this little clip, you can't quite see because I didn't have enough hands, but just before I took this, I was really trying to wring the neck of this XT crank in every direction apart from what would normally be pedalling torque, to see if I could get an output on their app, on their sort of diagnostics app for torque. And it was jumping around a little bit, but I couldn't get it to read over 1 Newton meter, even with really bending it against the table and putting all my weight on it. So the positioning of their gauges and their bending compensation was really good. We'll just go back a bit and try and play that video, although nothing really happens.
Take a video.
Yeah, you can't really see me bending it, but you will have to trust me. So I was pleasantly surprised at actually the bending compensation of those. Next one, don't really know too much about this, but quite an interesting application. This is the Verve infocrank. Surprisingly, this type of layout seems only to be a half bridge of strain gauges in each crank arm, because I can only see 2 wires coming from that little grid there in that cutout, and there'll be another one at the top. Now, this isn't ideal in terms of temperature compensation, but what they have done is by modifying the crank geometry, they can increase the strain resolution and sensitivity of the gauge, because by thinning out that bit and putting those 2 gauges further away from the centre line of the crank, they're getting much more bending strain when you apply torque than you would from let's say a Stages, which is measuring the shear strain on the outside. When you're applying torque, this is quite low, so this will give you a higher strain figure and a better signal than the stages, but I'm not sure how they deal with temperature compensation. By also getting into the middle of the crank and putting the strain gauges there, you also get closer to the neutral axis of twisting. So when I mentioned the load case about wringing the crank like a wet towel, if your gauges are in the centre of the towel, they won't see any strain. So the closest you can get to the twisting axis, the lower the strain is going to be. Apart from that, I don't really know much about the Verve. I think it's quite heavy, I think it's quite expensive. So finally, let's talk about calibration and how that changes between brands. So you've either got static calibration or dynamic, basically. So in a nutshell, calibration sets the gain or the slope and offset of the sensor reading. It forms basically a lookup table of torque and speed, so the computer can display the correct power output. Now gain or slope is factory set by calibration. It's the ratio of the output signal to the input signal. It could be expressed as watts, it could be expressed as millivolts per Newton meter, so when you strain the crank statically, how many millivolts is the circuit giving out? And offset is basically erroneous output of the sensor at zero input, which can be caused by long-term drift. Now this is user corrected on the head unit or automatically corrected in some cases, and it's often referred to as calibration incorrectly by media and even power meter brands. They say, oh, it's user calibrated. It's not. When you calibrate your power meter, people say calibrate it by spinning the cranks or pressing the Garmin or whatever. You're not calibrating it, you're re-zeroing it. So at zero input, the signal is zero, or the output, the watts or newton meters, is zero. Okay, so that's what people get wrong. Okay, so let's look at static calibration first. Static calibration can be done using calibrated dead weights hung off a dummy pedal spindle, or using a calibrated load cell, as seen above in the early 4 Eyes prototype. They actually use one of their own strain gauge sensors in their own load cell, which is quite a neat thing, but probably quite expensive. The problem with using dead weights is that there is some uncertainty of the length of the pedal spindle and where exactly the pressure from your foot is exerted. As discussed, the spindle creates a twisting moment on the crank, which could produce parasitic strains if the gauges aren't set up properly or aligned properly. And these parasitic strains, if they're not cancelled out, would falsely raise your apparent torque and power values. So when I asked stages about this, they said yes, it was assumed the pressure was exerted on average at the middle of the pedal spindle, and this is where they hung the static weights. But what happens if you use a longer pedal spindle like Shimano offer? I think you can get Ultegra pedals that push the spindle out another 4 mil, so your Q factor changes. Would that give you the same results, or would it induce a little bit more strain on the sensor? This is why parasitic bending compensation is so important. A much better way to do calibration is by use of a dynamic rig, which eliminates the pedal effects altogether. SRM and Power2Max both do this, but Power2Max only for NG, the high-end NG only, although they say they batch test NG ecos on the dynamic rig as well. This allows for much better replication of the real loading scenario, including all the tangential chain forces and sinusoidal loading of each of the spider arms at discrete angles of rotation. Obviously it's a longer and much more expensive process, but it's essential for the best accuracy. So that's the end of quite a heavy video, and that's just the electro-mechanical principle of power meter covered, and not even in full detail. That's only just the start of it. You've got to think about way more things, and this is why power meters are expensive. You've got another topic, electronic selection and optimizing of the circuits, PCB layout, coding, communication protocol to different sides of the power meter or to the head unit. You've got the AMP Plus protocol, Bluetooth, you've got app development, which everyone's doing now, you've got training of the workforce. You need really skilled labour to do strain gauges properly. It's not something you probably, well, I don't think anyone's doing it in China. It's all in-house. It's quite difficult to do reliably. You've got to have a QC audit system, you've got to have a service and warranty department, and you've got to build up a decent inventory, because this is a very quickly changing market. So from what was a niche product now becoming really popular, and everyone wants them over a set of wheels. So it's a very difficult position to be in to release this sort of product, and this is why the prices need to cover that. So I hope that's answered some of your queries and questions about kind of mysterious, maybe a mysterious product for some people, but yeah, hope I've shed some light on it for you. Cheers.